All right, so in 2.7, we're dealing with polynomial and rational inequalities. So again, there's typed up notes that I typed up. They're my notes, and it'll just be helpful if you read over those notes as you watch the video or before you watch the video. So what we're doing is we're essentially solving inequalities. So polynomials just mean we're going to have to deal with at this level, we're really only going to see polynomials that we can factor. So even though earlier in chapter 2 we were dealing with polynomial functions and everything's not factorable, for the inequalities, all your problems going to be factorable, okay? If you can't factor and you have to do quadratic formula, that's you spending time on something you should be able to factor quickly, because I'm telling you that all the ones you're going to get are going to be factorable for solving these inequalities, okay? So we have x squared minus 2x is less than or equal to 3. So before you can actually deal with the inequality component, you need to focus on being able to solve. So being able to solve here means that because there's an x squared term, it's a polynomial, we have to make this thing equal 0. So we're going to move the 3 by subtracting it on both sides. So we get x squared minus 2x minus 3 is less than or equal to 0. So when you're doing the inequalities, you just solve it as if it's just an equal sign. So we just go through and we solve normally. So x minus 3, x plus 1. So I factor it, and then I set each factor equal to 0, and then I solve for each x. So I get x equals 3 and x equals negative 1. Now there's two ways to work these polynomial inequalities. You can graph it on the real number line. You have to graph your solution anyway. But you can test values. So basically the 1 and the 3, we don't know if those are actually part of the solution. Now this was a less than or equal to. So in theory, they would be part of the solution because of the or equal to. So we just have to figure out where the solution set lies because it's an inequality. So we don't know where the solution is. So one thing you do is you test. So you split up your number line using the values you found x to be equal to. And so you're creating these barriers. And so what you're going to do is you're just going to test to see where you get a true statement. So like we're going to test in each compartment. So we test in each compartment to see if we get a true or false statement. True statements mean it's part of the solution. False statements mean they're not part of the solution. So if I try a number on the left side of negative 1, I would just try negative 2 here. I'll try 0 in between here, and I'll try 4. So what you do is whatever number you want to test, you're going to plug it in to your problem. And you can just substitute it in here. And whatever we get should come out as less than or equal to 0. 8 minus 3 is less than or equal to 0. 5 is less than or equal to 0. 5 is less than or equal to 0. 5 is not less than or equal to 0. That is a false statement. So what that means, if you get a false statement, that means that side of the number line is not part of the solution. So then I'm going to test 0. So negative 3 is less than or equal to 0. Negative 3 is less than 0. That's true. So that means that there is solutions between. The solution lies between the values. So then you can test the last one. -3. 8 minus 3. So 5 is not less than, so we get a false. So this is a false statement, which means that it's not part of the solution. So the solution here would be -1 to 3 in brackets because it was or equal to. Okay? Now, what the shortcut tells you is that you don't need to do all that testing. There's two things you can do to apply the shortcut. You can test on the left, the far left, and whatever you get all of your outcomes after that are just going to alternate. So what I mean by that is the first time when I tested the left side, I got a false. That just means my outcomes are always going to alternate false, true, false. So my true is in the middle, okay? The other way you can do it is you can just look at the original inequality symbol. My original inequality symbol is a less than. Less than automatically means that the solution comes together. So less than are considered and inequalities. So the solutions always come together and meet. If you have a greater than, those are always considered or inequalities, and your solution should go apart. So this started as an and, a less than, which means automatically I didn't have to test anything for me to know that the solution comes between the two values. If it was a greater than, I would have known my solution goes apart. Okay, so that's the shortcut way. So let's look at another one. X squared plus 2x is greater than or equal to 0. So on this problem, again, we're solving. It's already set equal to 0, so I'm good there. So now I just need to be able to factor this. So x squared plus 2x, I have a GCF. So then I just set each factor separately equal to 0 and solve. So x equals 0 and x equals -2. All right, so let me fix this. So I have components, right? I have different compartments that I would need to test. So for me personally, because I know that it's a greater than, I don't really need to test anything. I know that for me, my solution is going to go here and there because it's greater than, which means it's or. However, we're going to test just to show you. So if I tested in each compartment, so over here I could test -3, here I could test -1, here I could test +2. So -3 squared plus 2 times -3 should be greater than or equal to 0. So 9 minus 6. True statement. So here's what I know. I know if I started with a true, it's just going to alternate from there, which will mean it'll go true, false, true. Now, I'm going to just do it for you, even though I don't have to. But if I was to test the -1, that's how awesome math is. So -1 is greater than or equal to 0 is not true. That's a false statement. But I already knew it was going to be false because I'm telling you that whatever you do on the farthest left side, they will always alternate from that one. So because it came out as a true, it's going to alternate true, false, true. And it comes out perfect. But if you choose to go ahead and do test points, that's fine. 8 is greater than or equal to 0, true. So it works out. So what do I know? I already know that my solution is going apart. So from -infinity to -2 with a bracket because it's or equal to, union with bracket what? 0 to infinity. So your interval notation is what your solution comes from, just straight from your number line. So because I had a greater than or equal to, I automatically knew that my solution was going to come apart, was going to be two separate directions. So you just have to choose how you want to look at it. Do you want to learn a shortcut, or do you just want to test all your points on your number line? It's totally your choice. All right? All right, here's another one. Alright, so let's see, x minus 1 over x plus 8 is less than 0. Alright, so x minus 1 over x plus 8 is less than 0. So this is a rational inequality, but our shortcut rules aren't different. And these are actually going to be easy because there's no work to be done. You don't even have to factor anything. All we do is set each factor, because it's already in a factor form, set them separately equal to 0. So x is 1 and x is -8. you would do the same thing. You can plug it on the number line, and then you can do test points if you choose to. So what I know is I know this is the less than, so therefore my solution is going to come between. And I'm using just basic parentheses because there is no what? There is no or equal to there. So from -8 to 1. And if you chose to test, you could have tested. So we could have chose like -9 over here, 0 between them, and then like 2 over here. So if we test number -9, we would get -10 over -1, which would be +10 is less than 0, which is false. So that's false, true, false. So the middle is the true. All right. All right. And then x minus 3 or x plus 6 is greater than or equal to 0. So again, it's a rational inequality because it's fractional. There's a variable in the denominator. So we have to keep that in mind. So here we have a greater than or equal to. So whatever the x is, it can be equal to that, all right? It can be equal to it. So we do x minus 3 is 0, x plus 6 is 0. So we figure out what our boundaries are. Our boundaries are 3 and -6. So again, you can split it up or you can just know. So this was a greater than. So that means my solution is going to go the opposite direction. Now this is where, being a rational inequality, we have to have a second thought here. Just dealing with regular polynomials, we're good because basically there is no exclusion in a polynomial's function's domain. So basically the domain of a polynomial function is -infinity to +infinity because it's not one of the special cases. Rational functions, though. Rational functions are part of the special cases when you're thinking about a domain. So that means the solution, there can never be a value in the solution that has something that can make the function undefined. So when we look at this problem, and I was to do my solution set to this, my solution set would be -infinity to -6 union with 3 to infinity. The problem here is that if the x is equal to -6, because it's or equal to, and there's a bracket there, -6 minus 3, -6 plus 6 must be greater than or equal to 0. So -9 over 0. -9 over 0 is undefined, which means if the function, if the x actually is equal to the -6, it does not create a true statement because it makes it undefined. This is your special case here for rational inequalities. This is why they're going to give you this problem type, because they want to know if you understand your rules. You cannot have a value of x part of the solution that will create a 0 in the denominator. That means that your solution must be -infinity to 6 with a -6 with a parenthesis, and then 3 to infinity. Because if the x is actually equal to the -6, it will create an undefined outcome. So the function goes up to -6 but cannot equal -6 because the -6 would create a 0 in the denominator. Okay, so that's the difference between this first example and the second example. The first example didn't have an or equal to on it, so therefore it would just already be parentheses. So the -8 is not even included in the solution set anyway. Okay, so let's do it over as if it was. So let's say the problem was x minus 8 over x plus 8. X minus 1 over x plus 8 is less than or equal to 0. So we would set each component equal to 0. So we got our -8 and 1. Again, it's a less than, so I know my solution is coming together, but it's or equal to's. So in theory, there would be brackets. But here's what I know. I know that because it's or equal to, this -8 would make the denominator a 0, which would make the function undefined if it actually equaled -8. So therefore, the -8 cannot have a bracket on it. It must use a parenthesis. So the solution set here would be from -8 parenthesis to 1. So whatever value comes from the denominator, it can never have a bracket on it. So when you're doing your solution set for these inequalities, any value of x that comes from the denominator, it's like a vertical asymptote. The value could never actually be at that x. So you can never use a bracket on that value. Okay? So that's your solving polynomial and rational inequalities.